Okay, in this video, we're going to start talking about some of the more internal methods of detecting bias or diff, more accurately put. And the internal methods, like we mentioned previously, are methods that don't reference any external variables. So there's no criterion variable of performance or anything else to worry with. And as I mentioned before, one of the advantages of this approach is that you don't have to worry about your criterion variable being highly reliable, free from bias itself, et cetera. So one of the papers I posted in the optional reading was one from me and Scott Tony Dandel in the SciOp perspective some years ago. And we really kind of argue in there that if your test scores are the same and your performance scores differ, you'll get a different regression line in the Cleary model. So it'll look like you've got some kind of test bias. But one of the points we try to argue for is that really maybe nothing wrong with your test at all. I mean, after all, the groups are equal on your test. It's performance where they differ. And so, the Cleary model sort of assumes that performance is measured perfectly and that if your test scores aren't reflecting that difference in performance, there's something wrong with your test. We can argue that no, maybe in fact there's something wrong with your performance measure, and maybe that's why the performance scores are different when the test scores don't differ at all. Either way, you get a different intercept, and the query model says you've got bias. We try to argue that maybe you don't have test bias, maybe you've got some other problem in there. Anyway, the methods we're going to talk about today, including the IRT methods, are called internal methods because they don't reference any external variable. They only look at the group membership variable or whatever grouping variable you've got and the test scores themselves. And there's a few different methods here. I'm not going to go really into them very much. One of the most basic ones is to look at differential relative difficulty. So this is not looking at differences in difficulty. So it's looking at differential relative difficulty. And what I mean by that is that with kind of the most basic approach, you would just see if groups differ in the difficulty of the items, right? That's sort of the most basic approach. Are items harder for one group of people than another group of people? And if they are, the problem with that is it doesn't really tell you much. In other words, if it looks like tests are just harder for one group than the other, you don't know if that's a problem with the test or if it could just be differences in the mean level of ability or whatever else it is that you're measuring. So you really can't tell anything by that. But this method's a little bit different. It's differential relative difficulty, and what you do is you basically figure out the rank order of difficult items in each group. So for your majority group, you rank order the items in difficulty from easiest to hardest, and you do the same for your minority group. And what you're looking at then is not differences in the difficulty itself, but differences in that rank order list. So if an item looks really easy for one group and really hard for another group, but the other items all seem to, pretty much have the same rank order, then it might be an indication that something's up with that item. That item is sort of unusual in some way. The downside of this is that, again, it's not really a latent method. You're not estimating the latent trait in some kind of a latent method, which is typically preferred and better. So it's a little bit rudimentary, but it does give you some tools to look at perhaps some group differences in item difficulty, and that may be an indication that something is not quite right. Another approach, and there's really a whole class of approaches here called the ANOVA approach. And essentially, it's the interaction between group membership and item performance. So is there some kind of interaction between the item and scores in the item and group? So one kind of variant of this that's quite common is called the Mantel-Hansel approach. And this is something you'll see in educational research a fair amount. You don't really see it a whole lot in IO psychology, but it is something that most diff researchers are at least familiar with. It's a lot like a chi-square kind of approach, maybe a slightly more complicated chi-square where you're looking at a basic chi-square would look at the sort of the overall performance for the item and then kind of break that up by your two groups and look and see if there's any kind of interaction there between your scores and the group, and the score being either 0 or 1 and the group being group A or group B. And you'd have a 2 by 2 table and you could do a chi-square value just like you learn back in kind of undergraduate stats. Um, Again, that is not an ideal approach. The Mantel-Hansel goes a little further, and then it tries to get an estimate of the trait score itself. But I'm honestly, I'm a little rusty on the Mantel-Hansel right now, but it's not something really that is an IRT approach, so I'm not going to cover it too much here. And what I want to focus on today is the IRT approach at looking at differential functioning. So what we've got here is the uh, item characteristic curve that we've been looking at really all semester for two groups. We've got a blue group and a red group, and this is what diff looks like. So the hardest thing to get your head around is that tested diff and differential item functioning, which is, again, it's not exactly bias because the term diff doesn't make any assumptions about why this happens, whereas the term bias does make assumptions about why this happens. So we typically almost always use the term diff. But what we're seeing here is that the relationship between theta and the probability correct differs by the two groups. So this is not saying that the two groups differ on the item, that their scores differ on the item, or that they're different in the trait in any way. What it's saying is for a given theta, so if you have two people with exactly the same theta, for example, of 0, that they will have a different probability getting the item correct based on their group membership. So let's take a look at this item right here. At a theta level of 0 for this item, you can see if you're in the red group, your probability getting this item correct is only around 0.283, something like that. But if you are in the blue group, your probability of getting the item correct is actually more than half. It looks like it's about 0.6 or so. So clearly, this item sort of advantages in some way the blue group. People in the blue group are more likely to get this item right if they have the same theta level, and that's important, right? Now, there can be differences in thetas and things like that. So you can actually have this amount of diff, and the observed scores may not look like what you expect. If the two groups have the exact same distribution of theta, then we would see higher scores in the blue group because they have a higher probability of getting this item right. But the groups don't need to have the equal distribution of theta. And so you really can't make any predictions about observed scores because you don't know what the distributions of thetas are. What this will allow you to say, though, is actually something much more important. It allows you to say what you want to say, and that is for people with equal thetas, you have different chances of getting the item correct depending on your group membership. And that, again, I think is the hardest thing people have trouble with. So a lot of times when I see proposals for your projects and things like that, it'll be something like, well, we want to test for diff across two groups, genders, or what have you. And you can do that, but just be aware of what you're doing. What you're testing is for differences in the measurement process in some way, right? The relationship between theta and the item response, this item characteristic curve, differs for the two group. So it really doesn't tell you anything about the thetas in the two group. It doesn't tell you anything about the observed scores or anything like that. It's just looking at this relationship between the thetas and the probability correct. And really, there's not a lot of context under which that might differ. We'll look at some of them later in in this lecture, or maybe the next video, but there's nothing inherent just in knowing you have, for example, gender differences on a measure of whatever, maybe spatial rotation. There's really no reason to suspect that you'll have diff based on the gender differences, for example. What diff tests allow you to do is they allow you to sort of rule out the possibility that there's a problem with the test that causes that observed score difference, right? So sometimes you will see people test for diff, um, and they'll test for diff when they are, when they have observed score differences on some variable, but they'll do it more to just kind of rule out diff or bias as the source of that observed score difference, right? Because that's kind of what diff tells you, that the probability of response for the same thetas differ across the two groups, right? So going back to what I was saying earlier, if groups had the same theta here, what would we expect? Well, we'd expect the blue group to have higher observed scores because all things equal on the theta scale, the blue group has higher probabilities of getting the item right. However, what happens if, let's say, the red group has a really high theta and the blue group has a really low theta? Well, in that case, even though we have diff, if a bunch of the red people are piled up on this end, they're going to have high probabilities of correct. And if a bunch of the blue people are down on this end, they're going to have low probabilities of correct. And so you could still see higher observed scores for the red group than the blue group based on their thetas, even though there is this diff that seems to advantage the blue group, right? And again, this is an advantage for the blue group because it takes less theta. There's two ways to look at it. One is for the same theta, higher probability correct. The other way of looking at it is how much theta does it take to have, let's say, a 50-50 chance of getting the item correct. Okay, so if we go over to the 50-50 chance of getting that incorrect, the P of 0.5, and we scale over, you can see it just takes more theta in the red group to meet that 0.5. So that's another way to do it. You can either take the same x-axis point and go up, or you can take a common y-axis point and go over. And either way, you'll see that it takes more theta, right, in the red group than it does the blue group for the same probability correct. Okay, in the last slide, we saw probably the most basic form of diff. We saw diff with respect to the B parameter, and that's what we've got up here right now. So you can see it's essentially, keep in mind, these lines are dictated completely and entirely by the item parameters, right? You have the same base formula we've looked at all semester, and the only thing that differs across these two lines is in this case, the B parameter. So so in order to think about the nature of the diff here, really it's all in the B parameter. The slopes of these lines are the same, and the B parameters alone account for 100% of this difference here. Is kind of what you see. You can also have diff though based on the A parameter. So if you think about what we're talking about here, the B parameter of course is the difficulty, so differential difficulty across the two groups, but the same relationship to the latent trait. Or in this particular graph here, we've got differences in the A parameters. So the actual relationship between the latent trait and the item response differs between the two groups. And the difference is such that you have the same B parameters. So if you look at kind of the 0.5 point right here, this is a two parameter model, of course, that the B parameters are the same. They both have the same amount of data needed to get a 0.5 probability of response. But what differs is the A parameter. And so you get this sort of unusual situation again about the item being sort of advantaged for one group over the other at different levels of theta, right? So for a low theta, you actually have a higher probability of getting the item right if you're in the red group. So there's an advantage to the red group at low levels of theta. And the opposite's true over at high levels of theta. Over here, for the same theta, if you make kind of a vertical line here, you see you have a higher probability of correct response with the blue group. So the blue group's advantage in this area of theta, the red group's advantage in this level of theta, and you have differences in the A parameter. You can also have, of course, diff due to both A and the B parameters, and this is where it can get kind of complicated. So the lines may crisscross, they may not crisscross. They can do a lot of different things here, and this is just one example where you've got a slightly lower slope in the red group than you do the blue group. And again, the slope differences are a little bit like differences in factor loadings in that they're a little bit unusual. That means the item is more strongly related to the latent trait in one group than another. So for whatever reason, this item seems to function a little better in the blue group than the red group. But in any case, you can see that the A and B parameter diff can take on a lot of different complicated forms. And we're going to move over to the graphs Excel sheet here in just a little bit and kind of explore this a bit and look at what happens with the probabilities and the nature of diff as we kind of go through different scenarios, different item parameters and whatnot. There's a couple of common terms you'll see in the literature. You'll see the term uniform diff and you'll see the term non-uniform diff. And uniform diff is where where the item always favors one group or another. And this is almost always what we're talking about when we only have B parameter diff, right? So we have this situation here. This is uniform diff in that it's always better to be in the blue group here, right? There's no area of theta where it's better to be in the red group. You always have a higher probability of correct response if you're in the blue group compared to the red group. So this is uniform in that it doesn't vary by theta. It's always advantageous to be in the blue group. Non-uniform diff, however, happens or can happen, I should say, when you have differences in the A parameter. It doesn't have to happen, but it can happen when the differences in the A parameter. So here, this is non-uniform diff. This is the term given to it, again, what we already looked at, where it's better to be in the red group if you're down in this area of theta, but if you're somebody over in this area of theta, it's better to be in the blue group. So it's non-uniform. The nature of the diff varies by theta, right? Depending on where you are on theta. And in this one, it's technically like a non-uniform diff, I suppose, but these are pretty similar. So you could have, situations where you have differences in A parameters. You don't have what we might call non-uniform diff. It can be uniform, but generally speaking, if you hear uniform diff, you should probably think B parameter. And if you hear non-uniform diff, you almost always have some kind of A parameter, at least when we're talking about A parameter diff. So at least when we're talking about dichotomous items, there has to be an A parameter difference to get non-uniform diff. So the interesting thing about diff in this case is that different researchers have treated this type of diff as they differ in their opinions about how problematic this is. So if you think about this situation, it's uniform diff. Pretty much everybody agrees this item is not functioning the way we would desire, right? We don't want the situation. Diff is typically a bad thing that you don't want to see if you're a psychometrician. You don't want people in the blue group to have an easier go at this item than people in the red group for the same theta, right? This relationship shouldn't differ. And the extent to which it does differ, it always advantages one group over the other, and that's not a desirable property. For this type of diff, opinions are a little bit more split. Some people have argued that, well, if theta is sort of normally distributed, yeah, it advantages the red group down here and it advantages the blue group up here, but on the whole, it sort of cancels out, right? Across kind of the whole sample, there really isn't any diff on the item. Um, I tend not to think that way. I tend to still treat this as somewhat problematic. And the reason is if you take the interpretation that this is not a problem, that it cancels out, is a group level interpretation of diff, right? It says across the whole group, red group or blue group, there's really no advantage for one person over another. And that's a little bit like kind of what Thorndike did when we think about those external methods we talked about. But that's not really the approach that we typically like to use. I typically like to use an individual approach. And if you are an individual, which you are, right, and let's say you have a high theta, right, there is a clear advantage to being in the blue group for you. And that's really what I think matters is individuals in the sample, are they disadvantaged based on the group membership? And in this case, they clearly are. It's people in the blue group up here that are being advantaged and people in the red group being disadvantaged. And the opposite's true down here. But there still are individuals who really can't control their theta and what it is that are going to see a disadvantage on this item. So I tend to take the interpretation that uniform diff is and non-uniform diff are both problematic. Uniform diff, I think everybody agrees upon. Non-uniform diff like this, there's probably more mixed opinions on, but I think if you're looking at it from the perspective of an individual, that you'll see that this is, it's problematic. If you're up here, you don't care about the rest of this graph. It could do whatever. It's not really relevant to you. What's relevant to you is this graph, kind of where your theta is.